So, in the literature there are three popular ways of doing this. So, one I have already sort of indicated to you that here is your sort of wire. I am just going to split it by a small gap delta, and I am going to connect this to a generator which puts some voltage VA. So, this is at plus VA by 2 you can say and minus VA by 2, okay, and this distance is delta. So, that is one way. Take your RF generator and plug it into the middle of this wire. So, that is going to generate a VA. Now, remember this is not DC VA, right, this is going to be a voltage that is fluctuating at the frequency you want to radiate at, right. So, over here do I know EI? Inside this segment, yes, right, it is just, what is it? Yeah, that is it, VA by delta. And what is EI over here? So, I am chopping it. So, you are going to chop this up into segments, right, when you do MOM. So, what is EI over here? There is no voltage source there, it is 0, right, because I did not connect the voltage generator across that segment. It's going to generate this incident field only across, the voltage is only across one part of the wire, not everywhere else. So, EI over here is 0 and EI over here is 0. So, I mean you have your conductor like this, okay. So, do not think that I have split the conductor, it is one conductor and in the middle I have connected one RF generator, both the leads to it, plus and minus. Yeah, you take 2 points and across those 2 points you connect this, and so that is why I have shown the leads like this, one is connecting here, the other is connecting over here, right, across some gap delta. There is no break in the current, yeah, on the upper segments. Yeah, well, that is again a, should we say that is a statics approximation? Well, this is the sort of a, this is a model, remember it is not going to, it's not exact, but it is a model that gives you close enough results over here, okay. The length, so say that again. Then it is not equipotential. If, yeah, then you have to take recourse to your transmission line theory. But the point is that there is, due to this induced voltage over here, I mean due to this applied voltage over here, there is now going to be a current that is going to flow in the wire, right, and that current induced in the wire is going to produce another scattered field, which is what we have been calculating, and together they are 0 in the conductor. Okay. So, this is your delta gap, which is the easiest one to apply, because it is just, you can see the values VA by delta in the gap and 0 everywhere else. So, this column vector that you have, this is a column vector at all different ZMs, right. So, that ZM which is the center of this segment you put in this value, all other places you put 0, that is it, very simple to apply. Okay. The second thing is what is called this magnetic frill, which it is like a ground plane and a coaxial cable sitting on top of it like a monopole. And then what happens by image theory is, I replace the ground by the reflection of this, but there is one thing, I mean we will not go into the detail, but as a result of doing this I am left with a small magnetic current over here. Okay, so this thing is called a magnetic frill, right. So, this is ground and this is coax cable, and this magnetic frill, there are some equations for it which give you some EIZ over the entire length. Okay. We will not be using this, in this discussion, but I mean there is enough literature on it that you can look up magnetic field. And finally, the third thing, so these are both for a transmitting antenna. For a receiving antenna also there is an induced there is an incident wave that will produce an equivalent of a source. So, here is my antenna over here and there is some plane wave falling on it over here. So, in that case what will I write? EIZ equal to minus, why minus incident field? What is it? It's just the value of the electric field, no? V by D, what is D now? You're overthinking it. This plane wave is falling over the entire thing, right? So, there is a field that is already there at every point of this conductor and its value is going to just be equal to the value of the field at that point with one small modification. Remember, we are talking about electric field and I have drawn these arrows correspond to, these arrows correspond to the wave vector. Which way will the electric field be? In general, E will be like this, right, and H will be into the board, right. So, this is going to be the Z component of it, because remember we are enforcing this along, we started by saying along the surface or on the interior and along the Z axis only, we are only looking at the Z component. So, this became Z dot this E naught e to the minus j k naught Z cos theta. That is your plane wave without the omega t term. Yeah, I mean if you have different polarization, this dot product will be different. It's just what is the value of Z dot E naught. Whatever it is going to appear over here. And this is going to be non-zero at every point inside this. At every of your ZMs it's going to be the case. E naught is the amplitude of this incident wave that is coming to you. Whatever, it's given to you in the problem. That yeah, you just have to take the Z component of it and in your column vector over here, this guy, put in the values, because that is the extra electric field that is coming over here in addition to the scattered field due to induced current. Those are the two fields which are present in the conductor, which should together sum to 0. Okay. So, this was for the transmission case and this is for the receiving case.